Hi, in this video, we are going to continue our series on vectors and 3D geometry. And today I'm going to talk about dot product of two vectors and all the applications that you will encounter, right? So first of all, we start off by the basic definition. If you do a dot product of two vectors, the answer for that would be AB cos theta, where A and B are the magnitudes of the vectors A and vectors B, right? And here theta is the angle between the two vectors A and B. Angle between vectors A and B. Now, certain things to know here. Here, when we do a dot product of two vectors, the answer that will come out will be a scalar. This is a scalar quantity, and that's why it is also sometimes called the scalar product, right? Also, the angle between the vectors is denoted by this figure. So if both the vectors are starting from the same point, then this is A vector and this is B vector. This angle is theta. So A dot B is equal to the length of this vector, which is your mod of A, which is A, and the length of this vector, which is mod of B, which is B, and the cos of the angle between them, AB cos theta, right? Now, how do we understand this geometrically? So the geometrical interpretation of dot product. So you can think of it as a way to understand projection of one vector on the other. So let's say we have one vector like this, OB, and another vector like this, OA. This is your B vector and this is your A vector, right? The angle between them is theta. Now, what do we mean by projection of B vector on A vector? Projection of B vector on A vector. So what this means is, what is the component of OB in the direction of A, in the direction of OA, right? So if you think in terms of physical terms, if this is a force OB in this direction, I need the component of force OB in the direction OA vector, right? So usually the way we do it is the component in this direction would be the projection. So if you drop a perpendicular from B onto the A, this length, if we call this C, OC is the projection of OB vector on OA, right? And OC length is what we want to capture. OC length can be seen clearly from this right angle triangle as B cos theta. OC is B cos theta clearly. So the projection is equal to B cos theta. And how do I write cos theta here? We can say that A dot B was equal to AB cos theta. Therefore, cos theta is equal to A dot B divided by AB, right? So what is B cos theta? It will be B into A dot B divided by AB. And now this B and this B get cancelled and this becomes A dot B divided by A, right? So projection of the B vector on the A vector will be the dot product of the two divided by the magnitude of the A vector, right? So that is an important result that you should understand. I will summarize it here. Length of projection of B vector on A vector will be A dot B divided by the modulus of the vector on which the projection is made. Similarly, length of projection of A vector on B vector would be A dot B divided by B, right? So that is the meaning. Now, another way to state the same thing is if A and B are two non-parallel coplanar vectors, and if B is resolved in the direction of A, in the direction of A. Basically, what that means is we are taking the component of B in the direction of A. Then we can say that vector component of B vector in the direction of A would be B dot A divided by A. This is the projection, and then A unit vector, right? So this is the length of the projection of B in the direction of A, and this is the direction of A unit vector. This can also be written as B dot A by A, and A unit vector can be written as A vector by A, right? So this whole thing will become B dot A divided by A square in the direction of the A vector. So the vector component of B in the direction of A vector can be given by this expression or this expression. Both of them are the same thing, right? Now, what is the vector component of B in the direction perpendicular to A? So far what we have done is we have understood the vector component of B vector in the direction of A. So what we have done is this. B vector is this. A vector is this. I have figured out my projection. This is my length of projection, and this vector is the vector component of B in the direction of A. And this is coming out to be B dot A by A square multiplied by A vector, right? Now, what is the vector component of B in the direction perpendicular to A? So this component, what is that, right? So we can say vector component of B in the direction perpendicular to the A vector. Now, obviously, B vector will be the sum of the vector component in the direction of A plus vector component perpendicular to A vector, right? So B vector is clearly the sum of this vector and this vector, right? So if I want to find out this vector, the perpendicular part, I can just write it as B vector minus this, right? So therefore, our answer for vector component of B in the direction perpendicular to A will be simply B minus B dot A by A square into A vector, right? So this is subtracting from B vector the component that is parallel to A. So that will give us the component that is perpendicular to A, right? So this result and this result you should understand visually and be able to apply in problems, right? Okay, now the next thing that I want to look at is some properties of dot product. These are very easy properties to prove. So I will not go into the details of the proof of them. They are pretty obvious, but I will just list them out so that you know what properties we have. So if A and B are two vectors and L and M are scalars, then we can say, first of all, minus A dot B vector is the same thing as A dot minus B vector is the same thing as negative of A dot B. So the minus sign can be taken anywhere. That doesn't matter. The second property is minus A dot with minus B is the same thing as A dot B. The minus minus become plus 1, right? The third property is L times A dot product with M times B is going to be LM A dot B, right? So that is another property that you should know. Then we have distributive law also. Distributive law also works. For example, you can say B plus C dot product with A will be equal to B dot A plus C dot A. And The same thing can be written like this also. A dot B plus C would be equal to A dot B plus A dot C. The commutative rule is also true for vectors. So commutative property means A dot B is equal to B dot A. For dot product of two vectors is commutative because it's a scalar quantity and the value of both of these is AB cos theta, right? So obviously that will be commutative. Okay. The next property is if A, B, and C are non-zero vectors such that A dot C is equal to B dot C, then we have two cases. We can say that either A is equal to B, or we can say A minus B vector is perpendicular to C. The reason for this is pretty obvious. What you have is an equation A dot C is equal to B dot C. We can bring both the terms to one side like this, equal to 0. And by distributive property, this is the same thing as A minus B dot C, right? So how will we get the dot product of two vectors to be 0? One of them, either A minus B or C, could be 0 vector. And the question has already stated that C vector is non-zero. So A minus B could be 0 vector. So from there you get the case A minus B is equal to 0 vector. So that means A vector is equal to B vector. So that is one case. Or the other case is A minus B and C vector are perpendicular to each other. And if they are perpendicular to each other, the angle between them is 90 degree. And therefore the cos 90 part will become 0, and that will make this true. So you have two options here. If A dot C is equal to B dot C, either A is equal to B or A minus B is perpendicular to C, right? Okay, the next thing is how to calculate the dot product if the vectors are given in terms of components. So if you have vectors like this, A vector is equal to A1i plus A2j plus A3k, and B vector is given by B1i plus B2j plus B3k, then A dot B will simply be the product of the A1 B1 plus A2 B2 plus A3 B3. Why is this happening? Because if you take the dot products of I dot I, that will be 1, because it will be 1 into cos of 0. And I dot j is equal to 0. Similarly, I dot k is equal to 0. J dot j is equal to 1 and k dot k is equal to 1, right? So because of these results, and also k dot I is equal to 0. Why is I dot j 0? Because 1 into cos 90. The angle between I vector and j vector is 90 degree. So therefore these terms will disappear. So when you do the multiplication, you are simply multiplying each term with all the other terms. So when I'm doing dot product like this, by the normal rules of algebra, we will try to multiply every term with every other term. So A1i, I will do dot product with this, then I will do dot product with this, then I will do dot product with this one, right? When you do dot product of A1i and B1i, you get A1 B1. But when you do dot product of A1 I cap with B2 J cap or with B3 K cap, you will end up with 0, because I dot J is 0 and I dot K is 0, right? So similarly, if you do every term, you will end up with these three as your answer, right? So that is a way to find out the dot product of two vectors if they are given in terms of their components, right? Okay. The next thing is an important property. If A, B, C are three vectors, then what we can prove is A plus B modulus square is equal to mod of A square plus mod of B square plus 2 times A dot B. This is the first property. How do I get this? So think about it. If you do A plus B dot product with A plus B, right? So what should it be? It should be mod of A plus B by the definition of dot product, mod of A plus B, mod of A plus B, cos of 0, right? So this will become basically mod of A plus B whole square, right? Correct. And what is coming on this side? This side is becoming by distributive law. If you multiply it, it will be mod of A square plus A dot B plus B dot A plus mod of B square. That is equal to mod of A plus B whole square. So what I am getting now is that mod of A plus B whole square is equal to mod of A square plus mod of B square. And because dot product is commutative, this is 2 times A dot B, right? So that is the proof of this identity. And this is an important identity. You should know how it comes, right? Another identity that is related is mod of A minus B whole square. And that will come out in a similar manner as mod of A square plus mod of B square minus 2 times A dot B. The third result is what is the dot product of A plus B dot product with A minus B. You just do the simple distributed multiplication. It will be mod of A square plus B dot A minus A dot B minus mod of B square. So it will be simply mod of A square minus mod of B square, because A dot B and B dot A will cancel each other here. Similarly, we can find out what is A plus B plus C whole mod square. That will come by doing dot product of A plus B plus C with itself, and you will end up with mod of A square plus mod of B square plus mod of C square, and the three dot product terms, which will be 2 times A dot B plus 2 times B dot C plus 2 times C dot A. So that will come as the answer for this case, right? Now these are standard results. You should know how to get these results and also prove them, right? Now, corollaries to all of this is if you add scalars to the same results. So if PQR are scalars, we can find out what is mod of PA plus QB whole square. So how do I do that? I will do it like this: PA plus QB dot product with PA plus QB, right? Because these are two identical vectors, so the angle between them is 0. So dot product of these two is equal to this. So this will give us P square mod A square plus Q square mod B square plus 2PQ A dot B, right? So that becomes my result for mod PA plus QB whole square. This is coming from here. Then we get similar results if you have PA minus QB mod of this square. It will become P square mod of A square plus Q square mod of B square minus 2PQ A dot B, right? Then the third one is mod of PA plus QB plus RC whole square. So similar to the previous cases, we will get P square mod of A square plus Q square mod of B square plus R square mod of C square, plus now you'll get the three dot product terms. So it will look like 2PQ A dot B plus 2QR B dot C plus 2PR A dot C. So that becomes your final result from there, right? Okay. Now, what I want to show you are some properties that are basically inequalities that you get using the dot product rule or dot product definition. So this is point 7, and we have if A and B are vectors, then first inequality is modulus of A dot B is less than equal to mod A times mod B. And this comes directly from the definition because A dot B is equal to AB cos theta. So mod of A dot B is equal to mod of A mod of B cos theta. And mod of cos theta is obviously going to be less than equal to 1. So therefore, this becomes less than equal to mod of A times mod of B, right? And we have gotten the proof that we are looking for. So this is the first inequality. Then the second inequality is mod of A plus B is less than equal to mod A plus mod B. This is the same thing as the triangle inequality. However, we can prove it by the identity that we had seen earlier. So mod of A plus B whole square was what? Mod of A square plus mod of B square plus 2 times A dot B, right? Now, this can be written as 2 times A dot B will be mod of A square plus mod of B square plus 2 times mod of A mod of B cos theta. So clearly this part will be less than equal to 1. So this will be less than mod of A square plus mod of B square plus 2 times A mod B, right? Because cos theta is less than 1 and this part is equal to mod of A plus mod of B whole square. So what we are getting is mod of A plus B whole square is less than mod of A plus mod of B whole square. So from there we can prove that mod of A plus B is basically less than equal to mod of A plus mod of B. So that inequality is done, right? I hope you have understood the proof. We have squared it and we have written this term, which is an identity. And then we said that cos theta is less than 1. So we got a perfect square here. And then we get the proof. The third identity, which is similar to the first two, and it's an inequality, is this one. You can say mod of A minus mod of B is less than equal to, the modulus of the whole thing is less than equal to mod of A minus B, right? So again, you can prove this simply by triangle inequality also you can think of it, or it is anyway easy to prove by thinking of A vector, modulus of A vector as A minus B plus B, and using the inequality that this is less than A minus B mod plus mod B. And basically take this to the other side and you get mod of A minus mod of B is less than equal to mod of A minus B. So that automatically finishes the proof, right? Okay. Another set of results that you should be aware of is this one. If A and B are vectors, then we can say that mod of A dot mod of B is less than equal to mod of A dot B. Not, this is not correct. Mod of A minus mod of B. So we can say it like this, mod of A minus mod of B is less than equal to this, is less than equal to mod of A plus B, right? So this is the combination of the three inequalities that we saw earlier. We have already proved them. There is no issue here, but you should understand that this is the maximum possible value of mod of A plus B, mod of A dot B, and this is the minimum possible value, right? The proof of this is from the previous thing that we just now did. So this should not be an issue for anyone. Okay. Then uh, another important idea is the Cauchy-Schwarz inequality for three quantities. So because we know that mod of A dot B is less than equal to mod A mod B, if you write the vectors A as A1 I cap plus A2 j cap and A3 k cap, and B vector as B1 I cap plus B2 j cap plus B3 k cap, then putting the vector components together here, you will get mod of A dot B is A1 B1 plus A2 B2 plus A3 B3 is less than equal to mod of A is root over A1 square plus A2 square plus A3 square times root over B1 square plus B2 square plus B3 square. And if you square this, you will get the Cauchy-Schwarz inequality, which is very important in mathematical Olympiad problems and sometimes even in JEE problems. So this is less than equal to the product of A1 square plus A2 square plus A3 square and B1 square plus B2 square plus B3 square. The equality happens in this case when the two vectors are parallel to each other, or when you can say A1 by B1 is A2 by B2 is equal to A3 by B3. When we can say this, then the two vectors are parallel and the dot product of A dot B is actually equal to mod A mod B because the angle between them is 0 degree. So cos 0 happens. So that is the equality case. And this Cauchy-Schwarz inequality you should be aware of. The next thing that I want to talk about is if A is any vector in space, then we can always write A like this. Then A can be written as A dot product with I in the direction of I plus A dot product with J in the direction of J plus A dot product with K cap in the direction of K cap. So basically what I mean to say is A could have any three components, right? A could be like A1 I cap plus A2 J cap plus A3 K cap. So if I wanted to find the individual components of A in the directions of I, J and K, then what I can say is A dot product with I cap would give me what? Would give me simply A1. A dot product with J cap would give me A2. And A dot product with K cap would give me A3. So if you want the components of a vector in any three directions, in the directions of say I, J, K, then you need to do dot product of that vector with a unit vector in those three directions. So this is an important idea. It tells us how to split a vector in space into its three component directions. Right. Now, the next thing that we want to do is to use dot products to prove some geometrical results. To prove results in geometry. So this shows us how important the whole idea of dot product is, that we can prove non-trivial results in geometry using this dot product idea, right? So first theorem that we will prove is that angle in a semicircle is always 90 degree, right? So let's see how to prove this. So let's say this is a semicircle. This is my center O. And let's say we have an A point here, B point here, and a random point here on the chord as on the diameter as the chord. We have to show that this point, this angle is 90 degree. So our job is prove that angle APB is equal to 90 degrees. And we will do that using vectors, right? So let's take O as the origin. So this is my zero vector and A and B are diametrically opposite points. So if A vector is A, then B vector would be what? B vector would be minus A vector, right? because these are the endpoints of a diameter. This length is equal to this length, and they have 180-degree angle between them, right? So we know the location of B vector and A vector. Let's say the R vector's position coordinates or position vector of R P is R vector. Okay, so we are saying position vector of P is R vector and position vector of A is A vector, right? So now what is the PA vector? PA vector is basically OA minus OP. So that will clearly be what? A vector minus R vector, right? Similarly, what is the position vector for P, or what is the vector PB? Vector PB is from P to B like this, and that would be OB minus OP, right? So that will become OB vector is minus A vector and minus OP, so minus R vector, right? And now we have to show that the angle between PA and PB vectors are is 90-degree. So I can do dot product of PA dot PB, right? So PA dot PB is coming out to be what? A minus R dot product with minus A minus R, right? So let's see what happens. This is minus of mod A square and minus A dot R plus R dot A, and then you have plus R mod R square, right? So notice that A dot R and R dot A get cancelled, and you have minus mod A square plus mod R square, right? Now, mod of R is also the radius, right? OP distance is the modulus of the R vector, and that is also equal to radius of the circle. And mod of A is also the radius. So all of these lengths are same. So therefore, this is 0. And we are getting PA dot PB is 0, which means PA is perpendicular to PB, right? So a simple calculation is helping us prove that the angle in a semicircle is always 90-degree. Okay. Another thing that we can prove and show the application of vector ideas is in triangle ABC, the length of the median, through the vertex A, is half of 2b square plus 2c square minus a square to the power half. So basically, this is supposed to be half of root over 2b square plus 2c square minus a square. So let's try to do this proof by using vectors. So let's say we have a triangle like this. This is my vertex A, this is my vertex B, and this is my vertex C. And let's pick A as the origin. So this is 0, 0. And position vector of B can be given as, let's say this is alpha vector. And let's say this is your beta vector, right? And the median is to this point D, and AD is my median, right? This is dividing the opposite side in equal parts, right? So obviously the position vector of D would be alpha plus beta by 2. Alpha plus beta by 2, that is by section formula. So we know the AD vector. AD vector is alpha plus beta by 2, right? So we have twice of AD vector is equal to alpha plus beta, and therefore if I square this, and I will get 4 times AD mod square. What am I doing? I'm doing twice of AD vector dot product with twice of AD vector. That should give me 4 times mod of AD square is equal to, basically it will be alpha plus beta dot product with alpha plus beta, right? So that will give us mod of alpha square plus mod of beta square plus 2 times alpha dot beta, right? So far what we have figured out is that 4 times AD square, I will just write it here. I have gotten that 4 times AD square is equal to mod of alpha square plus mod of beta square plus 2 times alpha dot beta, right? So that is equal to mod of alpha square is basically the length of this side, right? And this side is called C in the triangle. So this is C square. Mod of B square is mod of beta square is basically B square plus 2 alpha beta is 2 BC and cos theta, right? Cos theta is the angle between these two vectors. So now notice by cosine rule, cos theta in the triangle would be b square plus c square minus a square by 2bc, right? So what is 2bc cos theta? 2bc cos theta is equal to b square plus c square minus a square. So here I can write it as c square plus b square plus b square plus c square minus a square. So I end up getting 2b square plus 2c square minus a square. And now I have this, so I can write mod of AD square is equal to 2b square plus 2c square minus a square by 4. And when you take square root, you will get the required length of the median. And we have proved that this is the length of the median. We did nothing. We just took origin as a vertex and took two vectors as b alpha and beta vectors, found the position of the endpoint of the median, and took the length of AD square by doing dot product, right? And that automatically gives us the formula that we desired, right? So basically, similarly, you can prove many properties of vectors like this, and you should be able to do that yourself. So try it out. You can prove many geometrical properties using vectors. The next thing that I want to discuss today is the idea of vector equation of a plane, but this time we will use the normal form of the vector equation, right? So the first thing is the equation of a plane at a distance p, where p is greater than 0 from the origin O, and perpendicular to the unit vector, perpendicular to the unit vector n cap is r dot n cap is equal to p. So we want to prove this relation. We want to prove that this will be the equation of the plane such that the perpendicular from the origin to that plane has length p and is right and is perpendicular to the unit vector n cap, right? The plane is at a distance p from the origin and is perpendicular to the unit vector n cap. So in order to understand that, we need to visualize this. So let's say this is my plane, and let's say somewhere here is my origin, right? Now, what we need to say is that the distance from the origin to the plane is equal to p, right? So from origin, I can draw a perpendicular to the plane, and this point is becoming my n, and this perpendicular distance is p, right? If you take a random point in the plane, some variable point capital P, then this vector np lies in the plane, right? We also have on vector's direction is n cap, right? On vector is along the n cap direction. So if on vector is along the n cap direction, if I want to write on vector, I will say it is on times n cap, and on distance is p, so it is p n cap. On vector is p n cap, and p is a variable point on the plane whose position vector is r cap. So obviously, if p is this variable point on the plane, then pn is a vector on the plane, and this pn vector would be on minus op, and that would be basically pn cap minus r vector. So that will be pn cap. So you can write np cap as r vector minus pn cap. Actually, I should draw a hat here because it's a dot, it's a unit vector. N is a unit vector, right? I know that this NP is a vector in the plane and ON is perpendicular to the plane. So therefore, ON dot NP should be 0, right? So I can write now Pn hat dot R minus Pn hat should be equal to 0, right? And that will give us what? P times R dot N minus P square N dot N. N dot N will be 1 is equal to 0. So you are getting P times R dot N is equal to P square. So R dot N is equal to P. So this gives us the equation of a plane because it represents a random point in the plane. To understand what we are saying here, if there is a plane like this, the perpendicular from the origin to the plane has a direction of n hat, and the length of the perpendicular is given by p, right? So basically, on vector is going to be, on vector will be p times n hat, right? And then a variable point p on the plane, this point p vector, p point is having position vector of r. So this part of it would be r minus p n hat, right? And we can say that this vector is in the plane, so it will be perpendicular to this vector. So we can say r minus p n hat dot product with p n hat should be 0. And from here, we will be able to prove that p r dot n hat is equal to p square, and therefore r dot n hat is equal to p, right? That becomes the equation of the plane in the normal form. Another way to write this in Cartesian form would be like this. So let the position vector of a random point on the plane P be x I cap plus y j cap plus z k cap, right? And the direction cosines of the perpendicular vector n hat of the plane are, let's say, L, M, and N. These are the direction cosines of the vector perpendicular to the plane. So the n vector, unit vector is L I cap plus M j cap plus N k cap, because L, M, N are direction cosines. So these are the components in the ijk direction. So we can say r dot n, if you calculate r dot n, that would be the dot product of this vector and this vector, right? That will be equal to p, because that is the equation of the plane. Now from here we can get x I cap plus y j cap plus z k cap dot product with L I cap plus M j cap plus N k cap, and that should be equal to the length of the perpendicular P. So you'll get Lx plus My plus Nz is equal to P. And this form of the plane equation is known as the normal form. Here L, M, N are direction cosines of the normal to the plane. normal to the plane. And the length of the perpendicular from the origin to the plane is given by P, right? So that is something that you should know. This is an application of the dot product. That's why I'm mentioning it here, right? Okay. Another point that I would like to bring about here is the vector equation of a plane passing through a point A, passing through a point A with position vector A cap and perpendicular to the vector M is, so I need the vector equation of a plane through a point A. A is this, and let's say origin is here. So this A's position vector is A cap. And this plane is perpendicular to the vector M. So M vector is like this, right? It is always perpendicular to the plane, right? Now think about it. If you take a random point on the plane P whose coordinate is R vector, so then the vector AP is a vector in the plane, right? So AP vector would be R minus A, right? Because A plus R minus A would give us R vector, right? So R minus A, this vector is in the plane and M vector is perpendicular to the plane. So the equation of the plane can be written as R minus A dot M vector should be 0, right? So that becomes my equation of the plane. Now, if you think about it, if I want to make a plane parallel to R dot N is equal to P, then basically a plane parallel to this plane would also be perpendicular to the same N cap, right? But the distance might be different. So it will be R dot N is equal to K, where the constant distance from the origin is different, right? So once you have understood the plane equation in the normal form, you can also find a plane equation parallel to the given original plane, right? Okay. The next point that I want to talk about is how to find the angle between two planes. Angle between two planes. So if pi 1 and pi 2 represent two planes, and if n1 vector and n2 vectors are the unit normal vectors, unit normals to both these planes, then the angle between two planes, angle between pi 1 and pi 2 is defined as the angle between their respective normals, as the angle between n1 unit vector and n2 unit vector, right? So obviously, since these are unit vectors, the angle between them cos theta is equal to n1 dot product with n2 divided by mod of n1 mod of n2, and that is obviously 1 and 1. So it is n1 dot product n2. So the angle between the planes is cos inverse of n1 dot product with n2. So the angle between the normals is the same thing as the angle between the planes, right? So that is something that you should know. Now, another point I would like to add here is family of planes. So if pi 1 is equal to 0 and pi 2 is equal to 0 are non-parallel non-parallel planes, and these planes intersect. These planes intersect in a straight line. Two planes always intersect in a straight line. There will be a line of intersection between two planes. Then the equation of any plane passing through the line of intersection to their line of intersection will be given by pi 1 plus lambda pi 2 is equal to 0, where lambda is a scalar quantity and lambda can be real numbers. So for different values of lambda, you'll get different uh, line of intersections and different planes passing through them. So this represents an infinite family of planes, all of which will pass through the line of intersection of the two planes, right? And now lastly, I can also talk about angle between a plane and a line. A plane and a line, right? So if my plane equation is r minus a dot b is 0, and the line equation is, and the line is r is equal to c plus t times d vector. Now remember, this b vector is normal to the plane, and here d vector is the direction of the line, right? So the angle between the two vectors b and d, what is the angle between b and d? Cos theta is equal to b dot d by mod b mod d, right? But this theta is the angle between the normal to the plane and the line. The normal vector is my b vector, and the line could be like this, d vector. The theta that we have found here, cos theta, is the angle between the normal and the line. So the angle between the plane and the line should be 90 minus theta, right? Notice this figure. This is the normal vector. This is the line which is parallel to d vector. So the angle that you get by cos theta is equal to b dot d by mod d is the angle between the normal and the line. So the angle between the plane and the line is 90 minus theta. So it is 90 minus cos inverse of b dot d by b mod d. And by properties of inverse trigonometric functions, this is simply sine inverse of b dot d by mod b mod d. Because cos inverse plus sine inverse for the same angle is going to be equal to pi by 2. So this is the expression that gives us the angle between a plane and the line. And you should understand the visually what it means and how we are getting it, right? Okay, let's look at a couple of questions to revise what we have done so far. Let's look at this question first. Let A be given by 2i plus 3j plus k. B vector be given by 4i plus j, and C vector is I minus 3j minus 7k. Find vector R such that R dot A is equal to 9, R dot B is equal to 7, and R dot C is equal to 6. So it is a simple dot product question. You can say R vector can be written as xi plus yj plus zk. And all you have to do is find out x, y, and z. So R dot A is 9, gives us an equation 2x plus 3y plus z is equal to 9. And from these two, you get another equation 4x plus y is equal to 7, and you get x minus 3y minus 7z is equal to 6. And if you solve these equations, you will get the values of x as 1, y as 3, z as 2. And basically, then you will know the r vector as I plus 3j plus 2k. So a simple application of the dot product. Let's look at another question. Question 2 says, find the unit vector orthogonal to 3i plus 2j plus 6k and coplanar with the vectors 2i plus j plus k and I minus j plus k. So first of all, you need to know what is the meaning of the word orthogonal. So when you say find a unit vector orthogonal to something, orthogonal means perpendicular, right? So let's say this is my A vector and this is my B vector, right? And C is 3i plus 2j plus 6k. This is my C vector, right? Now I need a vector. Let R vector is the unknown vector, which is coplanar with A and B and is orthogonal to C right? So if it is coplanar with two other vectors, then R can be written as x times A plus y times B. We have seen that in previous classes that whenever three vectors are coplanar, then one of them can be written as a linear combination of the other two, right? Here x and y are scalars, and we also know that R dot C is supposed to be 0. And we also have to find R, and R has to be a unit vector. So mod of R should be 1, right? So these are the conditions that we have to satisfy. So first of all, x times A plus y times B, if you put A and B as 2i plus j plus k and I minus j plus k, you get R vector is equal to 2x plus y I cap plus x minus y j cap plus x plus y k cap. And now I will check the condition r dot c is 0. And if you do r dot c is 0, you will get 3 times 2x plus y plus 2 times x minus y plus 6 times x plus y is equal to 0. And if you put this, you will get 14x plus 7y is equal to 0, from where we get y is equal to minus 2x, right? Y is equal to minus 2x means my r vector is becoming 0 I cap, y is minus 2x. So this is plus 3x j cap, and y is minus x k cap, right? And the r vector has modulus of 1. So the modulus of this vector should be 1. So that will be root over 10x square should be 1. So x is equal to 1 over root 10, right? Plus minus 1 over root 10 will come, and therefore my r vector is coming as plus minus 1 over root 10 3j minus k cap. So I have found my desired vector here, right? Okay. One other question that I wanted to show is find the equation of the plane. Find the equation of the plane through the point minus plus 3 minus 2 1 and perpendicular to the vector 4 comma 7 comma minus 4, right? Okay, so Basically, I want a plane through a particular point. This point is 3 comma minus 2 comma 1. So the position vector of this from the origin would be 3i minus 2j plus k. So the plane should pass through this point and should be perpendicular to this vector. So this vector, let's draw it like this. This angle is 90 degrees and this vector should be 4i plus 7j minus 4k, right? So if I take a third point in the plane whose coordinates are position vector is r vector, then I can say that if this point is called Q, then PQ line is totally lying in the plane because P is also in the plane and Q is also in the plane. So what is the coordinate of PQ vector? Or you can write it as QP vector. QP vector would be R minus position vector of Q, which is 3i plus 2j minus k. So this vector r minus this is totally in the plane. So therefore it will be perpendicular to QP is perpendicular to this vector, which is the normal vector, right? So 4i plus 7j minus 4k. So since this QP is perpendicular to this, the dot product will be 0. So what I can do is r minus 3i plus 2j minus k dot product with 4i plus 7j minus 4k should be equal to 0, right? So how do I simplify it and write it? I can write it as r dot 4i plus 7j minus 4k and then minus 3i dot this will be minus 12 and nothing else plus 2j into so plus 14 and minus k so plus 4 is equal to 0. So I'm getting 18 minus 12 6, right? So what I'm getting is r dot 4i plus 7j minus 4k is equal to minus 6. And this is my vector equation of the plane. Because r is a variable point, it is like xi plus yj plus zk. If you put that here, you can even get the Cartesian form. You'll get 4x minus plus 7y minus 4z is equal to minus 6. And that is the Cartesian form of my plane equation. So I hope you have understood how we use the idea of dot product to get the plane equations and all, right? Okay. Now, I want to look at a couple more problems. Right. Actually, I will stop at this point because all of the theory that I wanted to discuss is more or less done. What we will do is we will do a problem solving session soon, but the next class would be about cross product of two vectors. So today we discussed all the applications of dot product, the various ways in which we can use that. And in the next class, we'll go to the cross product and also look at some equations of lines and planes which involve cross product equations, right? So stay tuned for the next session. We will cover the theory for cross products and then move on to triple products later. So if you like the content, please subscribe to the channel, like the video, subscribe to the channel and share it with your friends. And that's it for this one. I will see you next time.